Okay, hello everybody. Welcome back to the Intercontinental Seminar Series on Gravity and Cosmology this week. So this week we are very happy to have Professor Dimitrios Giataganas from National Sun Yat-sen University in Taiwan, and today, so he is going to talk about black holes and photon rings. Let me briefly introduce Professor Dimitrios a bit. So he got his PhD from the University of Durham in the UK in 2009, and in 2021 he joined National Sun Yat-sen University as assistant professor, and now he's an associate professor in National Sun Yat-sen University. So it's very happy to have you here, and thank you very much for giving this talk. So the stage is yours, please.
Okay, thank you very much. Um, I'm very happy to give to you giving guys the opportunity to speak in the intercontinental seminars on gravity and cosmology. So today I will be discussing an alternative way to study the photon ring properties with fundamental properties of black holes. They're basically their quasi-normal modes, and we are going to do that with the Penrose limit plane wave geometry. And so that's something, one of the targets of the talks is I will be just describing the title. Okay, so let me set up the terminology for the talk, since I know that some of the notations may be different from gravity and high energy theory. So let's suppose we have a black hole here, and the black hole is wrapped by a photon ring or light ring, I will be calling it, that is composed of this unstable circular null geodesics. So for example, if I go to equatorial or if I have a static black hole, my equatorial unstable circular null geodesics will be my photon ring. Okay. Then we know, since this is composed of unstable circular geodesics, we know that after some time the photons they will escape to infinity, and that's why I painted here by hand. That was the best description I could do for the instability. And this instability is described by something that we will be calling a Lyapunov exponent. And this Lyapunov exponent, we will be attempting something that is already known in the high frequency limit to directly relate it to the quasi-normal modes of the black hole by looking at the Penrose limit. Okay, so this correspondence is not something that comes out of surprise, right? In physics, whenever we have an electromagnetic system, whenever we have a physical system, let's say you have an electromagnetic system or whatever, you can always send a probe to your system, and you can look the properties of your probe. If you have, let's say, a strongly coupled system, you can send a meson, or you can send a quark. If you have an electromagnetic system, you can send an electron. And you measure the properties of your probe in your system, and then you can extract important information about the system or the theory itself. So in that case, we are using some particular geodesics, we are using the null geodesics to probe some properties of the black hole itself. And this can be also naively thought in a way that if you send, let's say, some matter, right, if you let some matter to fall in the black hole, you let something, and then the matter in the direction to the black hole will interact, let's say, will cross the photon ring that is outside the event horizon, and after it interacts with the event horizon, maybe you can think it as keeping as these photons now having some information of the matter that fall inside, and then the matter will go to the black hole, it will excite the black hole, and the excitation of the black hole is described by the quasi-normal modes, the modes that they decay exponentially with time. Okay, so we will be looking at this correspondence from a geometrical point of view, a very simple and a unified way that is called Penrose limit plane wave geometry. So basically you can think, I will define it strictly later, but you can think this geometry as that's experienced by a spatial observer that has been boosted and moving very close to the null geodesics. And you can think it as this geometry as a zoom into the space-time near the photon ring. Okay, so I will be defining it. I will be defining this plane wave geometry, and I will be looking at their properties very explicitly in a couple of pages. Okay, but this more or less sets the terminology, and I will be coming back to describe all the definitions and the ideas that I'm proposing here. And something before I switch page, there is also some other questions that we will be going to ask in these talks. For example, are there any bounds that the general relativity or any other theory impose to the Lyapunov exponent? So this is also partly motivated by ADS-CFT and holography, because we know, for example, that quantum many-body system and quantum chaos, it is bounded. The Lyapunov exponent that describes a certain type of quantum chaos is bounded above. So we will be discussing here if there are any similar upper bounds in the classical Lyapunov exponent that describe these trajectories, and what are the physical implications as well. Okay, so let me start being more explicit. So this is the outline of the talk. I will introduce, I guess the introduction everybody more or less knows, but I will spend some time to introduce and motivate the study, and perhaps I will give you some information from the high energy mostly point of view about this classical Lyapunov bounds that may be useful gravitationally as well. Then I will describe the properties of the plane wave geometry. We will see that in a plane wave geometry almost everything behaves as a harmonic or inverted harmonic oscillator, and this very closely is related to unstable and stable directions when we are looking at the photon rings at null geodesics. Then I will have to, since I will describe the plane wave geometry, I will have to provide you, I will have to pick up, to choose some black holes and to give you some explicit results. Okay, and this is something that is also interesting. Here I will not be working with a particular black hole. I will be choosing a very generic class of black holes. For example, that includes Kerr, Newman, and Schwarzschild, and so on. And I will be presenting the results in a unified formula. Okay, and at the end, if I have time, we may skip it. Then I can ask a question about what information the photon ring includes and conveys in the holography. Now, let me just form a sentence here, and then we see if we have time, we discuss it further. We know that perhaps you have heard that in ADS-CFT you have a quantum many-body theory, quantum field theory, and this quantum field theory corresponds in certain ways with a gravitational system. Now, if the photon rings, if the photon rings, they convey important information about the black hole itself, perhaps also they can be thought as part of the holographic duality. Okay, I will be saying more things at the end if we have time to this direction, and then I will conclude. Okay, so let me use 3 slides now. Usually when I discuss about instabilities, people start asking. So we have the traditional definition of chaos, right? We know that the chaos exists when a non-linear deterministic dynamical system with non-periodic orbits has extra sensitivity to the initial conditions. Okay, and there are several ways to recognize chaos. One is called Poincare section. Basically, we look at the phase space of the system and how the phase space is filled by the trajectories inside. And another way, I will be showing you a particular example in the next slide. And another way that is related also to this talk is the traditional definition of the Lyapunov exponent. Basically, you take 2 nearby trajectories or geodesics, you let them evolve, and after a long time, and you measure if their divergence is exponentially or not. A positive, in this case, a positive Lyapunov exponent tells you that you have chaos, that your system and your theory is a chaotic theory. Okay. In practice, this happens. This is a classical example that many books start when they want to describe non-integral system and chaos. So you have this chaotic Helmholtz system. You see here the non-linearity in the Hamiltonian. These 2 terms here, that they are non-linear, higher order, and you see that if I take, for example, this system, and if I go to the phase space, at a particular energy, my trajectories, they look like this. They are well formed. And here is my Poincare section. You see there's a section of constant momentum. So I pick up the points that my trajectories in my phase space meet this plane. I pick them up and I just plot them here. So for example, this is this, and this is this, and this circular here, ellipsoid is this one. But as I increase the energy, since the system is chaotic, I take this image for the trajectories, which basically my Poincare section is basically more or less filled up with these points. And this is the signal of that the system is it has chaos and is non-integrable. Now let me just finish this introduction of the chaos. Here something that is perhaps less known is that even when I have these very complicated Hamiltonians, there are systems, even for these nonlinear terms, that they can be fine-tuned in such a way that the systems become integrable, and therefore they're not chaotic. For example, if I tell you this I had before, this is the Hamiltonian that I had before, is exactly the same, but here I have this C and D coupling constants or parameters of the Hamiltonian. You can think of them as parameters in this way. There are 3 out of the infinite values that the ratio can take. There are 3 choices, very well fine-tuned choices, that this ratio, when it takes them, the system is integrable. Okay, these are the 3 values. Then when your Hamiltonian is fine-tuned so that C and D they take these values here, the ratio, then your system becomes integrable and therefore there is no chaotic. So generally that means that even if you have a system with nonlinear terms, there are cases, is not guaranteed that is chaotic, and there is a lot of work on this direction in high energy theory and also gravity. But but our theory, we are interested about general relativity, and we know that general relativity is a very nonlinear theory, so is natural that I have what we have in general relativity chaos, and also it's natural that we have instabilities. Okay, so the particular interesting class of this geodesic that we'll be discussing is the photon cell, as we advertised already, and the Lyapunov exponents is also important measure, since it is expected to be measured experimentally with a high precision for astrophysical black holes. Now there is already a well-established and very well-known relation between the quasinormal modes and the null geodesics in the eikonal limit, and a lot of works in this direction. And also there is also something that, as I say here, perhaps I will not be discussing so much, that building on this correspondence between the photon rings and the black holes and the IDS-CFT, perhaps there is possible to formulate some holographic principle of asymptotically flat black hole. So this is all part of the motivation that I would like to give. Good. So this is now something that I would like to define the Lyapunov exponent that we will be dealing in this talk, and that will be the Lyapunov exponent on the instability. This is something that is I think quite well known in the gravitational community. All this is not something involved. It's just a definition of is matter of definition of what we have here, but we can go through it a little bit just to see the definition of the Lyapunov exponent. So if I take the evolution equations and I can write them in such a way, right, that I define h dx I dt, and then to analyze the stability, as you know, we have to linearize around the solution, so we end up having this matrix here with k is defined through this equation. What I have here, the solution, it can be written in this way. So if I plug this equation here, you can see that if I write this equation like that, satisfies the linearized equation. It's just a matter of writing. So, but what is important, I want to convey in this talk now, is that the Lyapunov exponent is defined in a similar way as I saw that in traditional chaos. So you have we take the large time large time limit, and we define it as the logarithm of the final deviation versus the initial deviations. Okay. So that's the definition of the Lyapunov exponent on the instability, right? That we are going to use in this talk. In fact, as many of you you know very well, since I know you are working on these topics, you can do this in a very generic black holes. For example, if I do it for equatorial orbits in a spherical symmetric static black hole, here I go a little bit fast. I just give you the answer. If I can write the equation for the radial direction as VR of R, and then the Lyapunov exponent turns out, if I just plug what I did before, is a second derivative of this effective potential here, over square root of the second derivative over 2, which is computed at the radius, exactly the radius of the orbit. Okay, so if I want to apply it, for example, explicitly in some spherical symmetric black hole, let me take this black hole here, right? This is my time, this is my radial distance, and this is my, let's say if I am in 4 dimensions, this is my 2 sphere. So the equation of motions are given, since I have 2 conserved quantities, Pt and Pf, by these formulas here, right? That's classical Hamiltonian mechanics, and then I can write down the equation of motion for the null geodesics that is confined, then are bound around the sphere. Okay, I have to set, of course, some conditions, right? That the second derivative and the first are 0, since I am moving at the circular bound geodesic, and what I get is that my Lyapunov exponent basically will be equal to the second derivative of this equation here. Okay, at the photon ring, at the radius of the photon ring, which here I call it RC. Now, if you want to see some numbers, I guess some more explicit result, I can relate it directly to the properties of the black hole. Let me take the Schwarzschild black hole. Okay, so this is my Schwarzschild black hole, this is my blackening factor, this is the horizon, this is the radius of the horizon, and what I do here, if I do exactly the same thing, right, is straightforward computation, I will get that my the photon ring radius is 1.5 times the radius of the horizon, of the event horizon, so my photon sphere is outside the horizon. That's something we are, of course, interested in. And my Lyapunov exponent will be equal to 1 over 27 m square. M square is the mass of the black hole. Now you see directly here, as you know very well, the Lyapunov exponent in this case is related to the mass of the black hole. Now I advertised in the beginning something that that it was interesting for me, that but perhaps also interesting for the gravitational community, that perhaps there may be interesting to look for bounds that the theory, general relativity, imposes on these Lyapunov exponents. So in this case, for example, I just try to motivate this bound, and this is also motivation for this work that we are doing, that you see that the Lyapunov exponent here, this is the orbital frequency, but for this talk maybe it's not so important. Let's focus mostly on the Lyapunov exponent. You see 16 over 27 k squared, so it's less than the surface gravity of my black hole. And if I want to express that, if I want to go one step further, if I express my Lyapunov exponent, if I want to express with the entropy, I also see that this is less than a number here over the entropy of the theory. Now you can ask the question, you can ask a similar question now. Is at any bound, for example, if I take a different black hole, is the Lyapunov exponent bounded in a certain way by the surface gravity, or is it bounded in a certain way by the entropy of the black hole? And this partly is motivated by the quantum chaos in many body system, where there people take some take the art of time order correlator. So perhaps I want to avoid saying many details, but they take a particular correlator, and they know that describes, that probes quantum chaos, and they find that in quantum many-body system, the Lyapunov exponent of the quantum chaos is always smaller than 2pt. T is the temperature of the system. Okay. So I will be, perhaps if I have time, then later we will be discussing a bit more about the quantum chaos in the last section and about out-of-time order correlators. But this is just to motivate that perhaps it's interesting to look also from holography for such kind of bounds in classical GR. And in fact, let me define before. In fact, this is happening. This has happened. Look, people have been looking about this kind of upper bounds on the Lyapunov exponents. So let me just define the surface gravity in case that somebody, just to make sure that all of us we're reminded of the definition. So basically, the surface gravity is I put an observer at the horizon of the black hole and is a measure from infinity of how much force I should put on this observer to be static, not to fall on the black hole, not to escape. Okay, and this is defined. Basically, it can be found that it's defined by the contraction of the covariant derivative of the Killing vectors, but for spherically symmetric black holes, it takes a very simple form, that is this one here, the derivative of the metric element versus ddt over grr. These are the metric elements along the time and the radial directions measured at the horizon of the black hole. So the surface gravity can be very easily, let me say like that, can be very easily computed in most of the black holes, and is also a very compact expression. It has a geometric meaning about having a static, putting a static observer on the black hole horizon. And this is, if you know that this is always equal to pt, to 2 pi times the temperature of the black hole. Okay. Good. So since we have defined now the surface gravity and we perhaps partly or naively motivated these bounds, upper bounds, people have been looking on this. I think there is by now there is, I think, quite extensive literature. So let's see one of these particular cases. Let me take a particle. Now I'm not discussing that this experiment here is for a particle. Let me take a particle and I put it on the horizon, close to the horizon of the black hole, and there create some instability. Okay, I can put an external force, an electromagnetic force, and I can create an instability on the Schwarzschild, let's say on the Schwarzschild black hole. If I do that in a Schwarzschild black hole, this has been done in this work here, you see that the Lyapunov exponent is always equal to 2p, is always equal to the surface gravity. Okay, so then there was a discussion how universal this bound can be, and if what is the physical meaning. So there was a lot of work to this direction, but then easily you can see that this is not a universal bound. Once you take a generic black hole, you know that the near horizon expansion, the near horizon limit of a complicated black hole is not so difficult to do, right? It has some unique characteristics. So you can work with generic black holes that they have charges perhaps in rotation, and what you get is in generic, let's say a generic formula, is that the Lyapunov exponent is equal to the surface gravity, all of them square, and then you get the expansion here. You see that you have A1 and A2. These are some functions, right? In the case of a Schwarzschild black hole, these A1 and A2, they are negative. That's why the Lyapunov exponent is maximum only at the horizon of the black hole. But you can see that if you have other black holes, more generic, you see that indeed these A1 and A2, they can be positive or negative. So there is no universal bound that you can set, at least for the particle geodesics. Okay, for the particle unstable points close to the horizon. And this we have proved for a generic black hole, and there are very specific examples that has been gone through and disproving and computing the Lyapunov exponent, disproving the universality of this bound. But still, this whole discussion motivates us to ask the question if there is any upper bounds on Lyapunov exponent of photon rings now. Okay, it's just a motivation that from classical gravity that it also gives us the right and the motivation to ask this question. Good. And the last part that I want to describe, and that closes this introduction and the summary and the motivation of this talk, is that the massless wave equation. So we know that if I take a massless wave equation, I can approximate in the large frequency limit the solution with a slowly varying, right, amplitude A and a highly oscillating phase, right, since I'm in the high frequency limit. And then I can solve this equation order by order. Okay, this is something that I am sure some of you you have already done. So if I solve it order by order, I can see that the leading order is just this equation here, right, which PM is defined through this derivative, and directly this implies that if I want my equation to be non-trivially, that PM has to be null, and directly is also directly implies that here PM satisfies the geodesic equation, and this sigma is the affine parameter. That all comes from the leading order equation if I try to just plug this solution here in the high frequency limit of the massless wave equation. Okay. Now the subleading orders happen something even more interesting. I see that the amplitude of the subleading order decays with exponential minus theta, where theta basically is the null concurrence of the null geodesics. So what does it tell me? Of course, this has also to do with some boundary conditions, but what does it tell me? That approximate solutions to the wave equation are related to the photon ring null congruence, like PM and theta, the momentum here and the theta, and the divergence. And the exponential divergence of the null rays, it determines the exponential decay of the quasinormal modes. So this is a generic statement about massless wave equations and the null geodesics of the photon ring. Okay, and if you want to see it, if you want to see what I have done here in this page so far, you can just see that I can express my solution in the high frequency limit as being exponential to some function here times exponential the overtone number n, and lambda is the same Lyapunov exponent that I have computed, that I have introduced before for the null geodesics. So the solutions to the massless wave equation can be written schematically in a form like this, where lambda here is the exponential decay of the solution of the massless wave equation, and also lambda is the Lyapunov exponent. Okay, so this is how the relation in this eikonal approximation in the high frequency limit happens between the null geodesics of the photon ring and the massless wave equation. Okay, more or less these are all more or less known, but I think that wraps very well what the motivation and what is known so far. So what are we going to do here? So here we are going to discuss about this relation between the null geodesic deviation and the wave equation through the Penrose limit plane wave geometry. So as I mentioned before, the Penrose limit of a generic class of space-times of the photon cell, it gives us a geometry that is called plane wave. I will just, the next slide, I think I have exactly the definition of the metric. So I think I need to define the Penrose limit. So you can think that I am boosting an observer that is very close to the speed of very close to move parallel to the null geodesics, and at the same time I have to recalibrate their clocks. So every time I am boosting them, I am boosting the observer, I have to do a commensurate rescaling of the coordinates of my system in such a way that my affine parameter along the null geodesic remains invariant. So it's a boost plus a coordinate transformation in such a way that my affine parameter remains invariant. Okay, and that's a way that I also get a regular space-time. Okay, so it's basically a geometry of an observer. You can think it moving very close to moving together almost with a photon, with the photons of the photon ring. Okay, Now, what happens in this plane wave limit geometry? Once I obtain this geometry that I am discussing, you don't have to do anything else. The geometry itself contains all the information about the correspondence. It can also explain the correspondence, and directly the geometry itself contains the Lyapunov exponent, contains also the quasinormal modes. Okay, and this is why the geometry, everything in this geometry becomes a harmonic oscillator or inverted harmonic oscillator. The robustness of this approach is that this framework can be applicable directly to a large variety of the black holes. So you don't have to do the computation each time for a particular black hole. You do it once for a particular set of black holes, very large one, and then you know the result. You just have to apply what is the, let's say, what is a particular metric to your final formula, because this formula relies heavily on the symmetries of your black hole. Okay, so let me perhaps give you some information about the black hole and about the plane wave geometry. So the question is, why do we care to discuss about plane waves? So imagine you have a black hole with a metric g. In this black hole, I have a gradient killing vector field, right? So imagine, for example, I have my u and v are my light cone coordinates. They are depending by t and phi. Phi you can think as a simultaneous angle with a u1 symmetry, and then you can imagine x1 and x2 as being r and theta, the radial coordinate and my polar angle. So if I have this, let's say, four-dimensional black hole, I can construct the plane wave metric that looks like this here. You see, it doesn't have the only unknown element here is the matrix Aij. Everything else is fixed. The metric Aij depends only on u, not on v, because I have a killing vector field. And you see I don't have dv square because I have a gradient normal field. Okay, so I have a metric, and I call it plane wave because if I take u equal constant, you see that I have a planar space. So this is the metric I am getting for my black holes, for any of the black holes, as a plane wave geometry. The only unknown part, again I repeat, is the Aij, the matrix Aij, that here is, if I get four-dimensional black hole, is 2 by 2. And it's also diagonal in most of the cases that we'll be discussing here. So what happened with this space? Let me, just to demonstrate it by example, let me compute the massless geodesic in this space-time along the transverse direction x. If I compute the massless direction, I immediately see, right, I have no v dependence on this metric, so I have a conserved conjugate momentum, and I can take as usual the static gates for u. And if I do just a simple Euler-Lagrange computation for the massless geodesics or any other alternative way you want to produce them, to derive them, you get that the equation of motion for the geodesics in this background is actually the equation of motion for a harmonic, non-relativistic oscillator with a frequency matrix Oij. Of course, it depends if I have a harmonic oscillator or inverted harmonic oscillator. It depends on the value of the components of the matrix Aij. Okay, so it can be negative or positive. I can have harmonic oscillator or inverted unstable harmonic oscillator. Okay, so but this is the equation irrespective of what particular geodesic I'm looking. And even more importantly here, I can do the same here for the deviation, for the divergence, for the separation.
Sorry, Dimitrios,
Yes.
may I ask one question before
Yes.
you? So when you write down this plane wave metric, so you say that you can write it from arbitrary black hole spacetimes metric. Is that correct, or do you have some limitations on the symmetry
Good.
of it?
So I have done it for black holes that they are axisymmetric.
Yeah.
They have Hamilton's Jacobi separability on the geodesics. They have
Okay.
they admit killing Janot tensor.
Okay. So it's not so if you just start with a four-dimensional stationary and axisymmetric without guaranteeing the existence of the Killing-Yano, can you do this?
No, I haven't managed to do it
Okay.
because you need to get the Killing-Yano. I will explicitly have the construction in a couple of slides.
Okay.
So in the way I do it, you need to construct a parallel frame that transports along the null geodesics, and to do that, the most convenient way to do that is to construct the Killing-Yano tensor, and all the construction is based on the Killing-Yano tensor existence. And the Killing-Yano tensor, as you know, is also related to the integrability of the geodesics and to its separability.
So there's no additional assumptions on asymptotic conditions, right? There's no asymptotic flat. Okay.
Correct. There is no addition. Okay.
Thanks.
Good. Thank you for the question. So then I can do the same for the deviation of the family of geodesics, and I think I should not go to too many details, and also time is running up, and also perhaps they are not so much interested, but the properties interesting, the details. But what is the important thing is here that the Riemann tensor, in this case, this is the usual equation for separation of the two nearby geodesics, and this is the covariant derivative along the curve. So what happens here is that the Riemann tensor has very few non-zero components, and if you work it out, then basically you get exactly the same equation. That this separability between the separation between two nearby geodesics, it is given again by the harmonic oscillator or the inverse harmonic oscillator equation. So bottom line, I compute geodesics or the deviation between the geodesics, I always get harmonic or inverse harmonic oscillator, depending on what is the value, the signature of these Aij elements. Good. Now this also closes the discussion about about the properties of the plane wave that I would like to present, and this is related to what we already said, that now it is if my spacetime satisfies the vacuum Einstein equations, then it is guaranteed that one direction will be stable and one direction will be unstable. And this can be seen very simply because here the only non-zero component of the Einstein tensor is this one, which is basically the trace of Aij. To satisfy this equation, if I don't have fluxes, extra fluxes or whatever, I have to take the trace to be zero. So that means that one direction will be always stable, one other will be always unstable. And if you are familiar with the instability of the photon of this photon ring null geodesics, you know that this is exactly what happens also in most of these cases. One direction is stable and one is unstable. So without even specifying, this is the important thing I want to perhaps say, to summarize, without even specifying what is the metric, what is my black hole, I know if it's a vacuum solution Einstein equations, but I will have one direction that is stable and one other that is unstable, guaranteed. Okay. Good. So I have presented, and this is related to the question by Chaiwu that he just mentioned. So I have presented that this is the black hole. This is a generic plane wave metric that I can construct for a metric G here. But what is the metric G that I would like to work in this talk? So I will consider a metric that is separable, that the Hamilton-Jacobi equations are separable, and is a stationary axisymmetric. Okay, so for example, this of course is just to give you an idea. Of course, it's not to remember anything here, but the metric tensor in this case can be written in this form where Ci is r dependent on r theta, and they factorize in this similar way. Then it has been shown that this metric, you can work bottom up, separates the Hamilton-Jacobi equation. Okay, and this is the trivial. By doing the trivial Hamilton-Jacobi analysis here, you do the separability ansatz, and you get two separable equations along r and along theta, right? And then you just, if you solve them, for example, let me focus only on the equator. I put theta here equal pi over 2, just for simplicity. I get two equations that are applicable for any background. So if you give me the exact form is not important. So here the derivatives, this is algebraic equations, are not differential equations. When you see derivative, I take the derivative and I just solve for b and kappa. These are basically the analog of the impact parameter and the Carter constant if you want to think about Kerr black holes. So you give me a black hole that is like this, but it can be parameterized in this way, the metric, which includes Kerr, Newman, Schwarzschild, Reisen, Nordstrom, and many other. And then directly I am giving you, which is straightforward, I'm giving you where the radius of the photon ring is by solving these algebraic equations here. Okay, for example, if you give me, let's say, the Schwarzschild black hole, and I put it here, I will get that the radius of the photon ring from this equation here, from these two equations, is 3/2 the radius of the horizon. Okay. This is a straightforward calculation, but I just want to say that everything, the analysis can be done for all the black holes at once. Okay. Good. So we know now where is the photon ring for all these geodesics, for all these black holes. What do we want to do? So we want to construct the Penrose plane wave geometry, and we want basically to find what is the matrix A that appears in the metric of the plane wave. So how do we do that? To do that, I need to find a frame that parallel transports along these null geodesics. And we know, right? We know that by definition, the geodesic parallel transports its own velocity. So I need to find basically a tetrad, right, of covectors that is parallel transported along the null geodesic, and one of them is the velocity, is the forward velocity. Now, if I find the second leg of this tetrad, that will be enough because I can construct the remaining two by orthogonality conditions. Okay. So what actually I'm looking, I'm having the velocity, I want to have one more. So it is known that the contraction of the Killing-Janot tensor with the velocity, is basically straightforward to see from these equations here, is parallel transported along the geodesic. So if I find the Killing-Janot tensor, then I know the parallel frame, tetrad, all the legs that parallel transport along my photon ring, then I can construct my plane wave geometry. Okay, so bottom line is that I am now looking to solve, to extract a subspace of this generic black holes that satisfies this equation here. Okay. So I do that, and then you have to take some. We have to take some answers, and you can also see this work here. And when you take some answers, you find that the metric that I have written before can be reduced in this form. So this is now the metrics that I am working to discuss the correspondence between the photon ring and the black hole quasi-normal modes. They look like that, where now I have alpha is the rotation parameter, the angular momentum, proportional to the angular momentum of the space. It can be 0, and delta is an arbitrary blackening factor. Okay, for example, if I have delta to be like this, then this is a Kerr. If I have delta to be this, then this is a Kerr-Newman, and so on. Okay, so this includes at least the class of the black holes that they have arbitrary rotation parameter and arbitrary blackening factor. Okay, so it doesn't specify what I do. And if I do that, this is the solution. The detail of the Killing-Janot does not matter, but it matters perhaps just to show you that the class of the black holes is very generic. And when I do that, I can construct the plane wave geometry. So obviously this also, I just flash it for the reason to see that once I know this Killing-Janot tensor, I can work up to all these equations, and I can just find what is this matrix A. So I have reduced the whole metric to a particular subclass, which I know the Killing-Janot tensor, and I don't have to specify exactly what is the blackening factor. I can compute the Killian tensor, the Killing tensor, and then this is enough to construct the plane wave geometry that is given here by this equation. What is the result? This is just to flash that this is possible to start building from the Killian tensor my plane wave geometry. The final result, if I do that, it takes the very simple form, the matrix that is given by this equation here. For example, now I focus only on the equatorial geodesic just for presentation reasons. If I do that, I will get that my metric elements of the plane wave geometry, this is diagonal in the cases I'm looking at, and they are given by this simple formula here, where R0 is the photon ring radius. Okay, delta is the blackening factor, and here I just take the derivative of the blackening factor. So this is here, this is just a number. Okay, this is function of R0, but for particular black hole, I know what is R0, and then this is just a number. So you see also that A11 is not equal to A22 because I haven't imposed now, I haven't considered that these are all Einstein equations with zero fluxes. For example, I can have numerous solutions here. If I take black holes that are solutions to vacuum Einstein equations, then immediately I will get A11 to be equal to A22. So for example, for static black holes, if I want to simplify and I want now to compute basically what is a quasi-normal mode, the behavior of the quasi-normal modes of the exponential decay or the Lyapunov exponent, I will get that my lambda square, the Lyapunov exponent, is given by this simple formula that I have here, and the orbital frequency by the other, by this simpler formula as well. So I have two compact formulas that I can now geometrically realize the Penrose, geometrically realize in the plane wave geometry, my quasi-normal modes and my Lyapunov exponents for the photon rings. Okay, so for different black holes, I just have to put different blackening factors. So but I want to demonstrate what I said so far for particular black holes. Maybe I will just flash to you two results, and then maybe I have to slowly finish. Let me just mention also the solution of the massless scalar wave equation in this Penrose plane wave limit geometry. Here I go a little bit fast, but if you just do this particular parameterization that is again straightforward, I will get the Schrödinger equation. And look here again that my Schrödinger equation will have the components Aij that will basically imply that I will have a quantum harmonic oscillator on the state direction, and in the other side I will have a mirror is exactly the same but with a negative value, inverted harmonic oscillator. And if I compute the solution on this plane wave geometry without taking any high frequency limit, directly I will get that my quasi-normal mode that is given by this relation here. N is the usual overtone number, and lambda is what I have shown you here, and is also the Lyapunov exponent for the photon rings. Okay, so this basically directly relates without having to do anything else. Once the bottom line of this I think construction is that once you obtain the plane wave limit geometry, directly you have a geometric understanding of the correspondence between the photon rings and your quasi-normal modes of a fluctuation of the black hole itself. So I don't have so much time, but I just flash perhaps two results, right? And just to plug inside the values, and I just show you how simple and straightforward can it be. For example, if I work with a Schwarzschild black hole, this is my blackening factor here, m is the mass, the angular momentum in this case will be 0, and directly I put it in the equation I showed you before. I compute that the radius of the photon ring is 3m, or 3/2 radius of event horizon, and then if I just plug it to these equations what I have here for the Lyapunov exponent, I will directly get that A11, let's say this A1 and A22 is 1 over 3m squared, that's a number, and then the Lyapunov exponent will be this one that I have here. Okay, so it's just direct substitution. That's why I don't focus so much. I just direct substitution of this equation of this function inside the formulas I have shown. Okay, and then there is a lot of work in these directions, and that's complementary and very recent one for Schwarzschild and Kerr black holes. For the Kerr black hole, I can do something similar here, and if I put inside my blacking factor of the Kerr black hole, I will get again A11 is equal minus A22 because that's a vacuum solution. That will be 3 over R0 square, very compact form, and then I can compute the Lyapunov exponent. And in this case, that's something perhaps I can comment, the Lyapunov exponent is larger than, is increased compared to the Schwarzschild black hole, and also it does not obey this bound that I was advertising in the beginning, that is less than the surface gravity. Okay, I can keep going and do that for other black holes, but perhaps it is not, you can ask me if there is any question on this. The bottom line is that it can be directly applied to all the black holes of this class in a straightforward way. But let me, before I finish, I have 2 slides and I think I am on time. So let me just say a few words that I would like to discuss on the possible bounds on Lyapunov exponent. So at the moment we are switching a little bit more gears, but perhaps the discussion is interesting. So the idea here is that since we are working with a unified approach, we can look for possible universal relations of the behaviors of the observers we are computing. Okay. Now, as I mentioned before, there is a very known quantum system, chaotic bound for quantum systems, right? Basically, this involves the out-of-time order correlator. So, what is this? Is the thermal average of 2 Hermitian operators, right? The thermal average of the commutator square of 2 Hermitian operators, and when you do that, you find that it has. It shows it can probe the chaos, and you can define basically in the same way that exponential lambda t, you can define the Lyapunov exponent for the quantum chaos, and then it turns out that at least for theories that they are static, they don't have rotation and so on, and chemical potential, the Lyapunov exponent is equal to the temperature of the theory up to some numbers. Okay, and this 2pt here, as you know, is equal to the surface gravity. So as we discussed a little bit earlier, people have been extrapolating this bound to the particle case, and it seems that it's not universal, right? But what it seems here is that if you express the Lyapunov exponent of the null geodesics in terms of the entropy, you can find that in all the cases, at least we have discussed, you can find that it's bounded from above with an entropy that is with the inverse of entropy that looks like this, and pi over 4 is just the upper bound. So it seems that there is, so this needs further study. If there is something more fundamental on this, for example, maybe GR itself pushes and forces this bound in a fundamental way, the Einstein equation wants. It seems that in the case that there exists a universal bound that this can be expressed in terms of the entropy. Okay, guys, I did something now. I don't know what I did. Sync please. Okay, I am finishing. So this is my last slide before I conclude, and then I want to discuss something last as an extra motivation on what we are doing. So we know this is a bottom-up discussion. So we know that from holography is a correspondence between quantum field theories, many-body quantum systems, and gravitational backgrounds. If you have a black hole, this is a finite temperature field theory. Okay, you can think as, of course, in particular limit, a strongly coupled system. But what is important, I already told you before that most of the systems, at least static, they maximize quantum chaos. So lambda in this correspondence, the Lyapunov exponent, is equal to 2p, the temperature of the theory. Okay. Now let us work in a bottom-up way. Let's suppose that what we have computed is the quantum chaos, the Lyapunov exponent, corresponds to an out-of-time order correlator of the quantum system. We don't know what is the quantum system. This is a bottom-up assumption. So my lambda that I have computed here, it will be 2 times pi times an effective temperature. So I know what is lambda, right? I have computed already, let's say for the Schwarzschild black hole, and I am computing what should be the effective temperature that satisfies this bound. So the effective temperature that satisfies this bound, in this case is given by 4 over 3 square root of 3, where times T, the time T is the black hole temperature, right? If you are doing traditional, just to let you know a bit of the traditional ADS CFT, let's say I have ADS spacetime, ADS black hole, then I will get that my T effective equal T. In this case, I get my T effective is equal 4 over 3 square root of 3, the temperature of the black hole. Then we come here and we ask, what is the interpretation of the T effective in this case? So here is the point. That's a very nice coincidence. If I write, as it has been done here, if I write the near photon sphere geometry as a Lindner spacetime, I can immediately see that the analog temperature of the photon ring, it is given exactly as the same temperature that I have derived if I assume that there is a holographic dual and this corresponds to the out-of-time order correlator. So this is a non-trivial evidence that the photon rings conveys information about the holography. Okay, and this is something that is expected since the photon ring, as we saw, is related very closely to the black hole, to fundamental black hole properties. Okay, so let me finalize my talk. So the Penrose limit offers an alternative generic formally to study near photon cell physics and its relation to black hole properties. I find this geometry, basically means I find what is the matrix A, and once I find this matrix A, I know exactly all the correspondence between photon rings and the Lyapunov exponent without further computations. The framework, I think that's the robustness of the framework, is applicable for a wide class of spacetimes, and this yields to some readily usable formulas depending on the parameter of the black hole. Okay, so this basically, I'll take the Lyapunov exponent to be depending on this blackening factor. And this can be, for example, I believe it can be also fitted potential use for real data or even for modifications of GR, for black holes that they are solution modification of general relativity. And since this is a universal framework, unified, then is useful for proving universal features and potential bounds on the theory, in particular possible upper bound of the Lyapunov exponent we are proposing here, and perhaps this is interesting to study further. And this is something I perhaps mentioned it quite fast at the end, but perhaps this is because the audience is more gravity oriented. So you can see that you can interpret the photon ring as an effective holographic horizon, and then you can ask the question, what information does the photon ring convey about the dual quantum field theory? And this is an active direction of research, and it's worthy to think also along this direction. So with that, I would like to finish and thank you very much. This is a picture from our university, which you are welcome to visit. Okay.
Yeah, thank you very much, Dimitrios. Very nice presentation.
Thank you.
Any questions from the audience? So maybe I can start with one. I have a couple of questions. Even we have discussed before in May. So, first of all, so in the last slide where you show the holography horizon that could be defined from this, yeah, this slide. So in this example, did you consider Schwarzschild
Yeah,
or
this is
some?
Varsi. That's good.
This is Schwarzschild.
Yes, this is Varsi. But I think for Kerr it should be, um, I believe is doable also for Kerr black hole. But this is for Varsi.
Mm,
Yeah, that's a very good question. I should have mentioned it. Yes.
okay. And yeah, so and the second question is that so I understand that you start with a metric that is very general with a Killing-Yano tensor. And so I was thinking about the possibility that if you relax the assumption that with such a Killing-Yano tensor, but or even relax the assumption of integrability of geodesics, but if you just start with equatorial orbits, can you write down the plane wave metric that describes the plane wave spacetime near the equatorial orbits for even more general spacetime?
So that is not clear to me how I can do it, right? Because in this case, even if I get myself constrained on the equatorial, I still have to solve some equation that looks like this.
Ah, okay.
So
That may not be consistent equations if you
yeah,
let's see.
but then it may be possible, right? Because in this case, you reduce your space time.
Yeah,
Basically, you get an induced somehow space
yeah.
time. So you are looking also only at one direction. Um, so that now it may be possible, but we have to work it explicitly.
Yeah, I agree. Yeah, because I mean in the presentation you only show the A metrics on the equatorial plane.
Yeah,
I know that you can have a complete components for off equatorial plane orbits as well. I understand that, and I
yes,
think perhaps those components would also depend on those S theta functions in your Kirinyano tensor.
of course, of course.
So yeah, that's why I was asking like if you start with a metric or induced metric that confine on only on the equatorial plane, can you do that? I mean, if this is possible, that would be even powerful in the sense that you can interpret the correspondence for more general space-time. Of course, it's only limited to equatorial plane orbits, but I think that would be also a very nice uh, direction.
Yeah, I agree. But in this case, you see, these space times are already very generic.
Right. I
And
agree.
they also they also include the modified gravity black hole solutions, right? I mean, because that's basically what you claim, what you want to have is this axisymmetric
Yeah,
symmetry and the separability. So, but
yeah.
I agree, if this is true, then if this is true what you suggest, it can be also much more generic. Okay.
Yes. Yeah.
Yeah.
Yeah. Thank you. Any questions from the audience?
Maybe I have one.
Yeah, please, Torben.
What would you think if, I mean, usually we have an accretion disk, and this accretion disk can also contain a plasma. What do you think? How would this affect everything?
You mean if I can express the observables of the accretion disk with respect to Penrose plane wave
I mean,
geometry?
or already when we have normal geodesics, like exactly solvable, usually it results in a dispersion relation. And of
Mhm.
course, when you have something like chaotic geodesics, I guess, or I don't know if you can call it geodesics, but it would also affect them in a way that most likely there will be some dispersion. How do you think how would the results change?
Well, I'm not sure if they will. So if let's make this statement that if the Penrose to see if I understand well your question, right? So here I am computing the Penrose limit, the plane wave limit geometry for particular geodesics that they are in the photon ring. Okay. Now, as long as I am looking at on the observables that they depend on the photon ring, then everything can be expressed with this matrix A here. Basically, this matrix A is just a number. Depends on the black hole. Any observable that depends on the property of the photon ring will depend on this A.
Yeah, so I guess when Tobin, if you consider integrable geodesics even after including plasma, I guess that's what you were asking. And I think that's the plasma parameters are going to enter this
Good.
matrix A as well.
Yeah, okay, so yes. So then if you consider something that modifies your metric like plasma, right, then here, as long as you are still inside, you can parameterize your metric by following these answers here, or to be more specific, these answers here. As long as you can write your metric in this form, then everything that I have said here applies directly. You have to find where you will directly see where is your black hole, your photon ring, and then how it is get modified, and all these parameters, they will enter in these equations here. So it's just a matter of direct substitution to what I have, as long as your background, your black hole background, can be written in this formula here, in this form. Okay. Did I? Do you have any complaints about my answer, or?
No, I was just curious because you mentioned something about chaos, and I mean, I worked with plasma before, but I would be curious how it would affect the structure when you have like nonlinear effects.
Yeah, one non-trivial stuff in when you have plasma is that you can rewrite the non-geodesic equations when you have plasma. You can rewrite the geodesic equations as a timeline geodesic equations of some effective metric, if I understand correctly. And so maybe but of course it doesn't guarantee that the effective metric has a Killing-Yarnold tensor.
Exactly.
It's not. Yeah.
So that will be the question, if you can write your effective metric in this form, right? But does it modify the blackening factor, or it modified more heavily the metric?
I think it's not trivial because it becomes a timeline. It's a massive particle geodesics. It's not a null geodesics. It's a massive particle geodesics of an effective metric. So I'm not sure how to apply this Penrose limit to that kind of scenario.
Yeah, one has to work it out from the beginning.
Yeah.
Because the construction here is only for the null geodesics, bound null geodesic, unstable of course, of a black hole with axisymmetric symmetry that has a Killing-Yarnold tensor. Okay.
Yeah.
Practically, you can, if this is all confusing, practically you can see that as long as I can write my metric up to coordinate transformation in the form that I'm listing here now, right? Then I can compute the plane wave geometry of the photon ring, and then directly I know all the formulas. But this is for null geodesics in this case.
Yeah, sure.
But for modified gravity, I believe that also works. For example, if you if you take a blackening factor delta that comes from modified gravity, the construction does work as well in the same way.
Yeah, I mean that depends really on the theories that you're considering because I mean you can easily come up with some theories of gravity beyond GR in which for example the solutions to rotating black holes do not have integrable geodesic
Yeah, of
dynamics.
course.
Yeah.
Yeah, of
So
course.
I think it applies only to just some limit theories of gravity. You can
That's
easily,
correct.
yeah.
That's correct. But in this case, you will not be able to write your metric in this form.
Of course, yeah, that's right.
You will not be able to write in this separable form already.
Yeah.
So in a bottom-up way, if you like, you just have to find a way to write your metric in this form, and then you can apply your solution.
Yeah, I agree. Any other questions? So if no, then let's thanks Dimitrios again, and let's stop
Thank you very
let's
much.
end the official section of this